Hey Math Nines, and welcome to the start of our 7th unit. It's going to be entitled Similarity and Transformations. It's going to be found on your Math Makes Sense 9 textbook on pages 314 to 381. Just want to quickly give people a refresher if you're maybe new to the channel or you just, maybe are just dropping in on this unit from scratch. A reminder that at the bottom of all these videos on YouTube, in the descriptions is going to be a link to the video, to the note package that you're going to see that I'm going to be basically playing in the bottom of the screen here. So if you want to get yourself a larger copy of that note package to have at home while you're watching this video, you can click on the link that's below. As well, you're going to see any homework that is associated with this or any other video that you see here on this channel. So without any further ado, let's get started with our topic 7 discussion today, talking about 7.1, which is going to be about scale diagrams and enlargements. Quite often, you'll have, this is something that really kind of plays in really well with science. If you remember back in Science 9, you did some, maybe some diagrams under a microscope, looking under a microscope, enlarging images that you've seen. You're obviously taking an image that you see that's very, very small under a microscope and then drawing it to a larger scale. And we call that drawing an enlargement. But what you need to do when you're doing diagrams like that is you need to kind of figure out what's called a scale factor. So if I draw an image, like let's say the original image is that big, let's say I grab, I don't know, a little rock or something like that, or a little bug, and then I'm going to draw it to this size, what would the scale factor be? So what is a scale factor? Well, the scale factor is essentially when you scale up an image or scale up, a shape, as we would do here in math, you're going to take the scaled length of the scaled up image, and you're going to divide that by the actual length of the original image or the original object. So for example, if I had a bug that was 1 millimeter in size and I drew it to 10 millimeters in size, I would basically take my scaled length, which is 10 millimeters, divide it by 1 millimeter, which is the actual length of the insect or the bug, and I basically have a scale factor of 10, which would equate to 1,000%. And I'll get to that in a couple of seconds. Up here on the board, we're going to stick to something that's maybe a little bit more math, maybe not so much science. We got some triangles that are drawn here. And we have a triangle here that's got side lengths of 6, 8, and 10. And then that is being enlarged up to a triangle that has side lengths of 12, 16, and 20. Now, most of you looking at those numbers could probably already figure out roughly what the scale factor is. If you look at any of the corresponding sides of these triangles, you've got the scaled size, which is 20 to the original, which is 10, or 12 to the original 6, or you've got 16 to the original 8. Now you could use any of these numbers to create the scale factor for the diagram. So in this case, I'm going to use 20 and 10. So if I take 20, which is my scaled length, divided by the 10 of my hypotenuse there, which is the length of the original hypotenuse, you're going to have 20 divided by 10, which is going to give you a scale factor of 2. Now I can write it down as a scale factor of 2, or I can convert that 2 into a percentage. Now you're probably well aware, or hopefully you're well aware, that percentage-wise, 1 is related to 100%. So if I had 2, I would simply take 2 times 100 to get my 200% scale factor. So those are basically 2 or 200 for the scale factor in this case, pretty much mean the same thing. In science, you'll see more of the percentage. So you'll see like a percentage scale factor, like I enlarged that image or I drew that image 700 times or 1,000 times more. I enlarged it to 1,000% over the original image. But you can use just integers to represent those percentages as well. So that's basically an introduction into what scale factor is. Now, today's scale factor is all about enlarging, making things bigger, as we did here. We doubled the size of that image. So again, that 200% scale factor. Below, I've got my crude attempt at doing a graph paper. that is something in this unit that you're going to want to keep in mind. You're going to want graph paper for potentially some of the assignments that you're going to be doing. Graph paper is certainly going to make your life easier when you have to draw images that are scaled up. I have drawn my best facsimile of graph paper here on the whiteboard for you folks at home. And you may notice, and it may be a little tough to see, but I'll kind of highlight it for you here a little bit better in a couple seconds. I've got essentially an original diagram over here, and then I've got a scaled diagram of that same image right beside it. And we're going to discuss that right now. Now, this diagram that you see here, if you want to have a better look at it, you can go to page 318 in your textbook. There is an actual diagram very similar to this in your textbook on 318. You can kind of follow along off of that page, or obviously you can take a look at the note package that I've linked to under the descriptions. You can kind of follow along here on the notes if you've got them at home, and then it might be a better look at what we're doing here. So basically, in this case, we have an actual size. Now, this is not on my board. It's not actually the real size of an SD card. If you look in your textbook, the diagram of that SD card is actually the real size of an SD card in your textbook. This one is obviously a little bit larger, but let's just assume for a second that this is actually the size of an SD card. Depending on what screen you're looking at, it might actually look very close to the size of an SD card, or maybe it'll be smaller like a micro SD card. But the point is, this is our original image over here. And you can see that we're using the grid section to basically line up the object. So in this case, I've got an SD card that on the bottom, and I'm going to just kind of highlight the corner points here so they're maybe a little easier for you to see at home. Here are my corner points. I got a little indentation there, but that might make it a little bit easier for you to kind of see the outline. So basically, we're going down here, diagonally across, and like so. But you can see that along the top, I can measure off my little grid sections on the graph paper. So I can see that I've got 3 across the top. I've got 4 down the side from here to here. I got 4 here. I've got 2.5 here, and then I've got this little section, which is a 1/2 and a 1/2, which is 1. And then this section here is about a 1 1/2. Now, if I wanted to scale this up appropriately, in this case, and if you look in your textbook, it's like the triangle above. We've actually doubled the size of this SD card. So by using the graph paper, it's very easy for me to kind of keep tabs on how many grids I need to make this object the right size. And I had to draw this from scratch a few minutes ago before I started this video. So I would have done a very similar procedure. So I started with the top, and I had 3 along the top. So what I did is I started here, and I know because I was doubling the size of this, I knew that 3 to double 3, I'm going to times it by 2. I now need 6 across the top in order to make it double the scale. So there's my 6. 1, 2, 3, 4, 5, 6 across the top. I know that on the side here, I have this area that's 1 1/2 grids in length. So I had to double that. So 1 1/2 times 2 would be 3. And I've gone 1, 2, 3, and there's my grid section there to there. Now the next section, I've got a 1/2 and a 1/2 here, which would be my little indentation. And that's going to basically be now, instead of a 1/2 plus a 1/2 is going to give me 1. And then if I times that by 2, I'm going to have 2 now. So now that section becomes a length of 2. And then down here, I've got 2 1/2, which would double out to 5 on this current diagram that I'm drawing. Is twice the scale, or at a 200% scale factor. So there's my 5. 1, 2, 3, 4, 5. Now I can kind of start to fill in the gaps a little bit easier. I've got 1, 2, 3, 4 across the bottom. So that's going to give me 8 on my double scale diagram, because I'm going from 4 times 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. Now it's a matter of just sort of kind of connecting the dots. Along this way up here, I've got 4 as well. So I should be going up to 8 on the side here. 1, 2, 3, 4, 5, 6, 7, 8. There's my 8 there. And then the last line I've got is a diagonal. Now my grid isn't perfect. In theory, if this would be a perfect grid section, this line would actually line up over that intersection point. But because I drew it by hand, my grid section isn't exactly perfectly aligned. But what you will notice is this diagonal here only goes across one of the grid blocks. This one actually goes across two of them. It goes across essentially this one here and that one there. So even that diagonal has doubled in length from one diagonal grid block to two diagonal grid blocks. Now again, if you look on the slide and if you're looking on at home, you can take a look that you can see that this is actually a perfectly scaled up version of the SD card. And in order for it to be a perfect replica to scale, you'll notice that every single one of the sides that I drew had to be to that 200% scale factor. If one of them isn't, then there's going to be an issue. Now, when I drew this originally, you'll notice along the bottom here, I kind of had to erase part of my grid. What I did is I tried to draw it off the bottom first, and then I found that when I came back up the top, that my one grid was down here, and I wasn't quite lined up to my position like I was supposed to be. And then when I double checked, I didn't actually scale this properly. The little indent, I hadn't scaled it properly, so I drew the SD card too far down, which means that it wasn't a perfect 200% scale factor on all sides. Some of the sides were 200%, but not all of them, and that's what caused my alignment to be off. So I had to erase that line and then draw the line one up to basically fill the percentage. But as you can see, when you're drawing these scale diagrams, unless you've got like a ruler, these grid papers are going to be really helpful if you're asked to scale up a diagram on a quiz or an exam, or when you're doing them on your assignments. Grid paper is certainly going to be the way to go. Well, let's continue on. That sort of gives you an idea of what we're dealing with as far as scale goes. But let's kind of continue this discussion a little bit more. So scale factor, as I mentioned, could be expressed as a percentage. It can be expressed as a decimal, or as a whole number, or it can be expressed as a fraction. So there are three ways you can express scale factor. In this case, I've got another triangle. I've got my PRQ triangle, which is essentially, I guess, equivalent to my SUT triangle here. You'll notice that my one side is 8 and it goes to 12, my 6 goes to 9, my 10 goes to 15. If you were to basically do the scale factors of all three sides of that triangle, your scaled side, which would be the second one, because we're going to assume that we're enlarging this, we're basically going from this original to that scaled version. By the way, if I was going the other way, it wouldn't be an enlargement, it would be a reduction. We'll be discussing more about reductions in the next topic of the unit, which will be 7.2. But in this case, we're going from the original, which is the smaller one, to the bigger one, which is the redrawn one, or the enlargement. So in this case, we're going from 15 over 10, because this would be my scaled length over my original length, which would be 15 over 10, which would be 1.5. If I did 12 over 8, it's going to be the same thing, 1.5. If I do 9 over 6 for my scale factor, it's again going to be 1.5. So I could write down the scale factor as 1.5, but I could also write it as a fraction. I could write that down as 1.5, or I could even write it down as 3 over 2. I could write that down as a scale factor as well. So technically, if I call this scale factor 3 over 2, or 1.5, or 1 over 1.5, not 1.5, that's also acceptable. Of course, all of those can be converted to percentages. So in this case, we're going to increase our percentage up to 150, right? Because again, 1.5 multiplied by 100 would give you 150 if you were converting it to a percentage. So all three of these, actually all four of these, are acceptable answers to describe the scale factor that you're seeing on that triangle there. Now, how do I know it's a perfectly scaled triangle? Is it 100%? Is it consistently 150% scale factor? I proved that because what I did is I checked all the measurements on all the sides, all the corresponding sides. I calculated the scale factor in all three of them. All three of them came out to 1.5. If they didn't, then it's not a perfectly scaled up triangle. It's not like a perfect enlargement of the original. There is an issue with the scale on at least one or potentially two sides of the object if the scale factor isn't consistent all the way through on all the sides. All the sides have to have the same scale factor enlargement in order for that to be considered to be a perfect enlargement of the original. One last thing, you may have noticed that all the scalings we've done so far, they've all been enlargements, and you may have noticed that all the numbers for an enlargement, the scale factors for enlargements are always higher than 1. So if you have if your scale factor, by the way, is 1, there hasn't been any enlargement. If you have a scale factor of 1, you're basically reproducing the object exactly as it was, the original size as it was originally. That would be like a 100% scale factor. Anything that's an enlargement is going to have a scale factor of higher than 1. Anything that's a reduction of an object, or if you make an image smaller, let's say you're scaling down a map of Canada, that scale factor would be less than 1, right? So I mean, let's say you're scaling down a diagram to be 50% of its original size. That object is going to, that scale factor for a 50% reduction is going to be 0.5, or it's going to be a half, or it's going to be 50%. So obviously the percentages don't count for that less than 1 or higher than 1. Obviously percentages are percentages. If it's a percentage, if it's less than 100, then it's going to be a reduction. If it's over 100, it's going to be an enlargement. But if it's a decimal or a fractional representation of the scale, then the one is basically the magic number. Anything higher than 1 is going to be an enlargement. Anything lower than 1 is going to be an actual reduction of that object. Okay, so let's take a look at this wonderful diagram. Actually, no, before we do the diagram, let's take a look at the numbers that are here. I got 1.2, 1.00001, 99.9999999, 28, 1/4, 1, 0.45, 7/8, 100%, 320, and 3/2. What I'd like you to do really quickly right now, before you look on your slide, hopefully you haven't looked here yet, tell me which one of these numbers, of these scales, represent enlargements. I'll give you about 2 seconds. You can pause the video right now because I'm going to go right into it. I'm not going to just sit here and wait for you. Pause the video if you need to try it out, and then I'm going to give you the answers here right away. Okay, again, the rule is any number, if it's a fraction or a decimal, if it's over 1, it's going to be an enlargement. If it's over 100%, it's an enlargement. So 1.2 is over 1, that's an enlargement. 1.00001, that's going to be an enlargement because it's higher than 1. 99.9999999 is below 100, so it's going to be percent. It's going to be a reduction, a very small reduction, but a reduction nonetheless. 28%, that's a reduction. 1/4, less than 1, it's 25%. That's a reduction. 1, again, is the magic number. If it's exactly 1, it's not an enlargement or a reduction. It's just keeping the object the original size. 0.45 is a reduction. 7/8 is a reduction. 100% is, again, keeping it the original size. 320 is an enlargement, and 3/2 is an enlargement. So only 4 of these numbers actually classify as enlargements. The numbers that are below 100% or below 1 are reductions. So these are, I'm going to mark those with X's. The X's are the reductions. So we've got 5 reductions there. And then which of these are neither enlargements or reductions? Well, we've got the 1 and we've got the 100. Those are just the original size of the object, so they don't classify as either a reduction or an enlargement. Okay, you're probably wondering why there's this diagram of a mosquito up here. It's this slide right here. We've got an enlarged diagram of a mosquito. I'm just going to pull these numbers off here so we're not kind of confused by what's going on with these numbers. The original length of this mosquito is 12 millimeters. Now, depending on what you're looking at home on your tablet or your phone, what you would need to do if you're looking at this slide is you would have to measure the actual slide. Now, I have a length that's written down on the slide. At home, when I'm looking at this on my laptop, that diagram, if I'm projecting that on my laptop and I were to physically measure it on my laptop, that mosquito comes across as 73 millimeters on my laptop. The original size of an actual mosquito that we drew there is it's a West Nile mosquito. It's going to be 12 millimeters. So if I was looking at it on my laptop, it would be 73 millimeters over 12 millimeters, and that would give me a scale factor of roughly 608%. But I'm not looking now at a mosquito that's on my laptop. I'm actually looking at a mosquito that I drew on this whiteboard, and I'm going to physically measure it for you right now. I'm going to physically measure it right now. I had a tape measure. Hold that thought. Tape measure's off to the side here. Live TV, folks. This is what happens. Here's my tape measure. Got it handy. Here we go. I'm going to measure it right here. Now I'm measuring this mosquito right now as a 9-inch diagram. Now 9 inches obviously doesn't match up to millimeters, so I'm going to convert inches to millimeters. How did I do that? I asked Siri. Siri helped me out with that. And basically I got that measurement, 9 inches on my diagram works out to 228 millimeters. So this quick little sketch that I drew today, 228 millimeters in size. The original mosquito is 12 millimeters, so that's going to be my original size. So to get my scale factor, it's going to be 228 divided by 12. And that's going to give me a scale factor of 19. So 19 and it's actually an integer. It's not even rounded up. It's actually 19 on the dot. Didn't plan it. That was just the way I drew it. That would work out to about 1900%. So this mosquito you're looking at here on my board, from what I'm seeing, is 1900% enlargement. Now, if you were at home and you wanted to, if you're looking on a computer screen right now, I mean, technically you go to your computer screen, pull out a tape measure, measure that line, and see what scale it is on your end. I mean, obviously it's going to be a different scale than what I'm looking at because you and I are not in the same room viewing this at the same time. So keep that in mind, is that it's a little tough to sometimes visualize scale when you're watching a video because what you're seeing is not necessarily the scale that I'm seeing here. This mosquito to me probably looks way bigger than it looks to you right now at home. But if you had to measure it off your screen, you could measure the scale factor off your screen and you would get a different number than I would based on the measurement that you got of your mosquito at home. All right, almost there. Almost done this topic for today. Here's some more graph paper. And I'm getting better at this apparently. So what I've drawn up here, and you can see it up here in the corner, I've drawn a little L shape. There's the dots for the corners, and you can kind of connect the dots there. You can see I've kind of shaded it in a little bit. What I'd like you to try to do, if you have some graph paper at home, and you can pause me here right now, is get your graph paper out, draw yourself a little L like this. It's going to be 1 block by 3 blocks by 3 blocks by 1 by 2 by 2 is going to get you that shape, and you can kind of follow along with my grid at home. I'd like you to pause me in a second here, but what I'd like you to draw, I'd like you to draw 2 of them. I'd like you to draw one that's going to be a scale factor of 150, and then I'd like you to draw one L that's going to be a scale factor of 400. So try both of those at home. See if you can plug away and see if you can do it. Pause me right now, and then I'm going to show you kind of what I did on my end. All right, here's what we're going to do. Now that you've done that, hopefully you have done that at home because obviously this is good practice for you. I'm going to go 1.5. So I know that in order for me to have a 1.5 scale, 1 is going to become 1.5. 3 is going to become 4.5 because I have to times it by 1.5. 2 is going to be enlarged by times by 1.5 as well, so that's going to be 3. So here's what I'm going to do. I'm going to start off with my first line here. I'm going to draw 3, which is going to be times 1.5, which is going to be 4.5 grids now. So 1, 2, 3, 4, 4.5 is right there. There's my one side right there. I'm going to thicken the line so you can see what I'm doing. The bottom is 3 as well, so that's going to be 4.5 because it's 3 times 1.5, which is my scale factor, right? 150% is 1.5. I'm going to go 1, 2, 3, 4, 4.5 is to there. There's my second line. My next line up here is going to be 1 times 1.5 is going to be 1.5. So I'm going to go up to here for that side. It's going to be 1.5 in width. Now this becomes 2 times 1.5, which is 3. So 1, 2, 3. I have to be careful because I'm halfway through a block now. So I've got to go 1, 2, 3 to there. Now the rest is going to be pretty easy. I mean, now at this point, if you're kind of good at drawing, you're going to pretty much know that up here it's going to be 1.5 as well because this is 1 times 1.5 is 1.5, and then pretty much I've only got one side left, and I'm going to connect those dots. Now I'm going to double check to make sure that side is in fact the right scale. I've got 2, which is now becoming 3. 2 times 1.5 is 3. There is a great scaled up 1.5. This is a 1.5 scale version of the L. There you go. Let's do the 400% or the 4.0 scale factor of this. Everything gets enlarged now by multiplying by 4. So I'm going to start it right here because this is where I'm going to need to, actually I'm going to double check here so I don't run into graph paper. I am going to go, I need 8 at least here. So that's going to be, I might not have enough room to do this. Well, we'll see what happens. I'm going to play this by ear. So I'm going to go down here in the bottom corner just so I don't run out of room. I'm going to start off with this side here, which is 4. So I'm going to start off at the bottom. I'm going to start off with this side right here, which is 1 times 4 is going to give me 4. So the beginning of my thing is going to look like this. That's the side of the bottom of the L. This is going to be 1, 2, 3. 3 times 4 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can see the problem here. I didn't have enough graph paper. I'm going to overlap a bit of my other diagram, but you bear with me because obviously, this is sort of live TV, right? Or at least it's live for me, pre-taped for you, of course. That's going to be 12. I've got 1, 2, 3, so I need 12 up the side. 3 times 4 is 12 again. 1, 2, 3, 4, 5, 6, 7. Hold on, I gotta count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 brings me up to there. I'm going to have a little bit of an overlap over my 1.5, my 150. I should have maybe drawn that one up there, but that's okay. Not a big deal. On the top here, I've got 1 multiplied by 4 is going to give me 4. There's my 4 right there. Now I've got 2 down the side multiplied by 4 because it's a scale factor of 4 is 2, 4, 6, 8. There's my 8. And if I've done this correctly, in theory, this dot should now line up straight to that dot there, and it does, which is great. I'm going to double check though. I should have, on the side here, I've got 2 times 4 is 8. I should have 1, 2, 3, 4, 5, 6, 7, 8. Look at that, perfect. And then I just fill that in. And then there you go, ladies and gentlemen. There is my scaled up L at 400%. So that's my 400% scale right there. This one here is my 150. And this guy here is my original, which we started with. Ladies and gentlemen, there ends the lesson. There's your stuff on the page if you want to look at it in the notes. I didn't flip that up earlier. There's all the diagrams there. And before we go, if you want to see a quick recap video, take a look at this one here. This will give you a quick little kind of, I guess, if you need a little bit more help, maybe I can confuse you on some of these topics because heaven forbid I don't do that enough in class as it is. Take a look at this video up here to give you a kind of maybe a little bit of extra help with scaled up enlargements and stuff like that. The homework for tonight, which you can email me as per usual, you're going to complete practice questions 4, 5, 7, 8, 11, and 14 on pages 323 to 324 in your Math Makes Sense 9 textbook. That is it for today, folks. When you join me next time, when I discuss basically the opposite of enlargements, which is drawing reductions. Until then, have yourselves a great one, and we will see you soon.